Imagine you're ordering food on Swiggy at 8 p.m. on a Friday night. You place your order, but wait. Friend sitting right next to you opens their app and see your order already placed. How? You just clicked confirm 2 seconds ago. This isn't magic. This is data replication working at millisecond speed across distributed systems. And if you can't explain this in your MAANG interview, you're leaving money on the table. I'm Arpit and I've spent decades of building distributed system at multiple companies. Today in next 45 minutes, I'm going to teach you exactly what Google, Amazon, meta engineers know about data replication, the concept that separates them from $150K to $350K packages. Here's what makes this different. I'm not just going to show you theory, I'm going to show you how to think about these problems the way L5 engineers do. By the end, you'll be able to design replication strategies that can handle billions of users. So let's get started. Before we deep dive, let me show you the roadmap for today's session. We're going to cover 4 major pillars, and I'm structuring this exactly how a MAANG interviewer thinks about replication. The first one is leader follower replication. This is the foundation. This is your safety net for 90% of the interview questions. Then we have replication lag problems. This is where good candidates become great candidates. Understanding these nuances shows system design maturity. Then we have multi-leader replication. In this advanced territory, this separates the middle-level developer from a senior-level thinking. And the fourth and final is leaderless replication. This is the elite level. You can mention about DynamoDB, Cassandra, and you'll see the interviewer's eyes lit up. Each section builds on the previous one, so don't skip ahead. The magic is in understanding why we have evolved from simple leader-follower to the complex leaderless systems. So let's start with the fundamentals. Here's a question that stumps 60% of the candidate in a system design interviews. Your database just crashed. You have 10 million followers who are trying to use the data. How do you ensure that there is zero downtime? If your answer doesn't involve replicas, you've already failed the interview. Let me show you why leader-follower replication is the backbone for every major tech company. This is your leader node, and you can also call it master or primary. Every write operation or every new Instagram post or every Amazon order, every Gmail email goes here first. Then we have these are followers. You can call them replicas or secondaries or slave. Although this is an old term, we don't use it anymore. So when someone writes any data to the leader, it is copied to the followers. Now here's the beautiful part. When you read data, when you scroll Instagram, you check Amazon order, you can read from any of the followers. But when you write a new data, it has to go through the leader and flow to the followers. It cannot be the other way around. So for leaders, whenever we do writes, it is done through leader only. But if we read, it can be from leader or any follower. This is how Netflix serves 230 million users. This is how Instagram handles 2 billion accounts, the leader-follower replication. Now here's where it gets interesting, and this is a direct interview question which I got in one of the FAANG interviews. Should replication be synchronous or asynchronous? Let me break this down in the real-world scenario. For synchronous, we have a client which interacts with leader, then the leader interacts with the follower, and then we get an acknowledgement, and after the acknowledgement we get client response. So imagine you are sending a photo on an Instagram. With synchronous replication, your photo goes to the leader first, and then after going to the leader sends it to the follower. After that, follower sends an acknowledgement to the leader. Once it receives an acknowledgement from the leader, then only leader will tell you the post is success. So some of the advantages of this is we have strong consistency. In strong consistency, if the leader crashes right after your photo has been uploaded to the follower, it is still safe. So even after the leader crashes, you can still get back your photo. And it guarantees that there is up-to-date data in the follower. Then some of the disadvantages, I would say, it's very slow. So for instance, you're waiting for a network round trip for the follower, and if the follower is down, you won't get success response till the follower comes back up. And because of that, you can sometimes be blocked. Now let's discuss about asynchronous replication. In asynchronous replication, the client first sends the request to the leader, and then the leader sends it to the client immediately after it has saved the data. So we can write in the background, what happens is the replication starts. So what happens is leader sends it to the follower in async format. So this is kind of a background job. Let me take the same example which we use for Instagram. You post a photograph and your photograph goes to the leader. Then the leader says, I got it and post successfully. Then in the background, the leader sends the photo to the followers and the follower eventually update. So some of the advantages are we have fast writes. And then if the follower is down, then also the leader continues to function. Now the disadvantages can be if the leader crashes before it has sent it to the follower, then we have actually lost the data if the leader goes down. Now the followers might be seconds or minutes behind. This creates a replication lag. We will discuss about this in the next section. So now some of the real world use cases could be, first is in banking apps. Here we cannot lose money, so it is preferred that we have a synchronous strategy. Then we have social media. Most of the stuff in social media is asynchronous because speed is of more priority than perfect consistency. Then we can discuss about e-commerce. In e-commerce, we have hybrid form of replication. For critical data, we use synchronous, whereas for non-critical, we use asynchronous. Now, here's the secret most of the companies use. That is called semi-synchronous replication. In a semi-synchronous replication, we wait for one of the follower to confirm or acknowledge, and then the leader can update that the update is successful. In the meanwhile, the other followers asynchronously replicate the data. So the balance is between the safety and the speed in this case. So that is why MySQL calls semi-sync replication. This is what PostgreSQL recommends. This is what you should recommend in the interviews. Your database has been running for 2 years and you are adding a new follower. So how does it catch up the 2 years of data which is already there in your database? So let me draw this scenario for you. So we have 2 years of data in a DB. That is a leader. Now I want to introduce a new follower. How do I catch up this data? So you cannot simply start replicating your data from now on. The new follower would miss 2 years of data. Here's the standard process. This is asked in 30% of the system design interviews. Step 1 would be take a snapshot. What we need to do is take a consistent snapshot of the leaders database. In PostgreSQL, this is pg_dump. In MySQL SQL, this is MySQL dump. And it is important to note the exact position in the replication log when you take this snapshot. Then we do step 2. Here we copy the snapshot to the new follower. In this, we transfer the snapshot. For large databases, it might take few hours to a few days. So what happens is whenever we take a snapshot in this case, so we have taken a snapshot. This is the snapshot version from certain timestamp, and then we copy it to the new follower. Then step 3 is catch up replication. In this, what happens is the follower requests all the changes since the snapshot position. The leader sends the new changes and then the follower applies. The new sends the request for the delta changes, and then the leader sends the delta changes which the new follower can apply. Now, after the complete copy has been done, step 4 is normal replication. In this step, once we caught up, the follower operates as a normal follower. It is not anymore a new follower. Mention that during the snapshot creation, you use technique like snapshot isolation to ensure data consistency without blocking writes. This shows deep understanding. So here's a nightmare scenario. The number one reason why the distributed systems are hired by the FAANG and the big tech company is that suppose it's 3 a.m. and the leader node crashes and there are 10 million users who's trying to access the data. What happens now? There can be multiple scenarios of failure. Let me take each one of them one by one. So first scenario can be a follower failover. In a follower failover, the follower fails. So let me draw this for you. We have a system that is the leader, then we have followers. Now, suppose this follower fails. What happens is the read goes to the other follower. So in this case, the read, instead of going to this follower, it doesn't goes anymore to this. It goes to the other followers now. Now there can be a scenario 2 as well where the leader crashes. In this case, it is called a failover. Let me draw the arrow for you. In this case, the leader fails and we can remove the... So there are a couple of steps which we do for a leader failure. First is detecting the failover. In this scenario, the followers notice that the leader hasn't sent any data for 30 seconds. So even if there is no data from the client, the leader keeps on sending a heartbeat kind of data every few seconds to all the followers. And in this case, if the threshold is 30 seconds, then it is assumed that the leader is dead. Step 2, we choose a new leader. In this case, all the followers, after deciding that the leader is dead or not available anymore, they choose a new leader. There can be 3 types in this case. The first one is election process. The second case can be the manual process. And the third can be pre-configured controller nodes. So in an election process, the follower decides a new leader among themselves. This can be used by doing a raft algorithm, or Zookeeper does the same. Then a manual process is like intervention by an administrator. This process is a bit risky and slow. In the pre-configured controller nodes, it decides which node to be put as a new leader. After step 2, we do step 3, in which we promote a follower to the new leader. So what happens is, once the leader has failed, out of all these followers, we have a new leader. So this is the new leader. So this becomes. Then we have step 4, where we reconfigure the systems. In this step, the client needs to send the new writes to the new leader. This is often done through a load balancer or a service discovery like console or etcd. So the client now, instead of sending to the leader, which was the old leader, now it sends to the new leader. All the requests are directed to the new leader. Okay. There can be certain critical challenges which can come up with the election process. So let me put that for you. One we can have is that there can be a data loss. So whenever a new leader is elected, there might be a chance that the follower doesn't has the latest data and it hasn't yet been replicated. In that case, there is a data loss. Another is split brain. What if the old leader comes back online and thinks it is still a new leader? Now there are two leaders, so that is why there can be a data corruption. So this scenario is called split brain. To solve this solution, we can use a technique called fencing. So whenever the old leader is forcefully coming up and deciding it to be a new leader, it is forcefully shut down. Third can be a timeout settings. If the timeout setting is too short, then there can be false alarms or unnecessary failovers. And if it is too long, then there can be a long downtime. So these are some of the challenges which we face during the failover scenario. You can always mention about consensus algorithm like Raft and Paxos to elect the leaders safely. This shows a staff level or a principal level thinking. Now the final piece of leader follower. How does the leader actually sends the changes to the followers? This is technical, but understanding this separates you from 80% of the candidates. The first method could be statement-based replication. In this, the leader logs SQL statements, something like insert into user and then update statements. Now the problem with this situation is whenever we use non-deterministic function, they can have an arbitrary value. So in this case, certain functions like now and rand, which give the random values, this can change. So this is an old approach and I don't recommend this for the interviews. Second method is write ahead log replication. In this, the leader writes changes to the log before applying them to the database. And the log contains low-level details. It could be in the form of the bytes and the blocks in the memory. And that is copied to the follower server. And this copy happens at the byte level. Some of the advantages, like it is used by Postgres and Oracle. Now the advantage is that we have the exact replication that is on the leader. So the leader and the follower has the exact data. Now the disadvantage here is the data is tightly coupled to the storage engine. So we cannot replicate across different storage systems. This is one of the major disadvantages. Now the third method and the final is logical row-based log replication. In this case, the leader logs the changes at the row level. So in this case, for example, if there is an insert value, we log the exact changes what the values are being put into the database. Or if it is an update value, we log the primary key and the columns change, what was the exact value of the column that was changed. And if it was a delete value, we log the primary. Now, why this is the best approach? It is decoupled from the storage system. Then we can replicate across different database versions. We can send data to external systems like data warehouses and caches, and it is used by MySQL, binlog, Postgre, logical replication. Now I'd use logical replication because it is version independent and allows heterogeneous replication, which is important for microservice architecture. Here's a question that exposed my understanding gaps early in my career. Why did the user just report seeing their comment disappear after posting it? So they posted a comment, it showed up, then they refreshed it and it's gone. Then 5 seconds later, it appears again. Actually, this isn't a bug, this is a replication lag. And this is the number one cause of subtle, hard to debug production issues in distributed system. Let me show you 3 critical problems with replication lag, and more importantly, the solution that make you look like a senior engineer. Now let's discuss about the core problem. Writes to the leader at t is equal to 0 seconds. Suppose the leader takes 5 seconds to copy it to the follower. So it takes 5 seconds. In the meanwhile, another user B, tries to access the write from follower B at t is equal to 2 seconds. Now, since it hasn't yet been replicated and it will take around 5 seconds, at the second it will get the stale data. So this is called a replication lag. Now, if the user reads from the follower between T0 to T5, they see old data and the change hasn't yet received yet. So how do we solve this problem? Because this is what a asynchronous replication is happening. Because of the eventual consistency, the user might see the old data. Let me give you a real world example. For example, a Twitter. When you tweet, you immediately refresh. Sometimes you don't see your own tweet. Why is that? You write to the leader in US East DC, but when you refresh, your read is from a follower in US West. That's 2 seconds behind. So this is where there are 3 problems that might occur. So let's discuss about the first problem, that is reading your own writes. Now let's say Alice sends a photo to the Instagram. So you'll have Instagram, and this Instagram writes to the leader server. Now what happens is the leader server is connected to multiple follower servers. Once the read happens, Alice sends another request, that is to read her comment. Now this time the Instagram tries to read from one of the follower where the leader hasn't yet replicated it. So what it sees, the old data here. Because of this, she's not able to read her own write, because it might take 5 seconds over here, or maybe it might take 10 seconds, and Alice read it after 2 seconds itself. So this is a terrible UX. User expects to see their own changes immediately. Even if other users can wait for 5 seconds, you must see your own changes. Let's discuss about some of the solution strategies. So, strategy 1 can be read your data from leader. In the scenario, what we do is if the user is trying to read its own data, it will read it from the leader. Otherwise, if they are trying to read someone else's data, they will perhaps read it from the follower. So it will be like if user reading route read to lead. Now else route to any follower. In this case, how do you determine your own data? For user, you can find out the user ID from the request body or the request URL and then route it to the leader. Otherwise, if the request is from other users' data, then you can route to a follower data. Second strategy we can have is monotonic read. This we will discuss in the later section. Strategy 3 can be track your replication position. In this, when the user writes, leader responds success and responds the position in the log. So for example, if the position of append is line number 12,335, it will respond the position number. So the next time user tries to read its own data, it will send I want the data from position 12345 or later and not before that. That way system routes to a follower that is at least at a position of 12345, right? So this strategy is used by LinkedIn and you should mention this in the interview. Strategy 4 is sticky sessions. In sticky session, all the users' reads and writes are routed to one single follower or server. So for example, if user A wants to read or it wants to write, all are routed to the server B if it is connected to server B. So they happens on the one server itself instead of routing to different server. That way, even one more thing is maintained, that is causality. Now, as per the interview perspective, and if you are applying for a staff level or higher positions, you can say that for read and write consistency, I'd implement a strategy where user reads their own data from the leader for 60 seconds post write and then fall back to sticky sessions with a preferred follower. This balances consistency with scalability. This answers you understand the trade-offs and it is suitable for a position that is L5+. Now the second problem we are going to discuss about is monotonic reads. Suppose Bob is trying to read a data. We have three follower servers. One is FA, then FB, and we have F. So these are the three followers which are connected. Bob tries to read the comments on YouTube. So first time he reads from FA and he gets back 10 comments. Now again he tries to refresh the screen and this time the server it routes to is FB, where he again sends a read request and it gives 8 comments. Third time maybe it goes back to FA or it could go to FC also. In this case, it might return maybe 6 comments. Do you see the problem here? Right? He sees different comments every time. You see, this time it sees 8 comments. Then here from FC, it sees 6 comments. So the monotonic read says that once you see a data, you should always see that data or the newer data. You should never see the older data. Now to solve this problem, we have few strategies. So one strategy to solve this issue is using sticky session. Now in a sticky session, the user ID is used to determine the follower. It is hashed to one of the follower and then it is consistently read from that particular follower. If that follower suddenly breaks down or goes down, then it is remapped to the new server. This uses consistency hashing. This uses consistent hashing. This is very simple, and this way you will always maintain that whatever data you have seen, you will always see that, or you will see the newer data. So some of the advantages what I see here is it is very simple to implement. Now the disadvantage is that if the follower dies, right, it has to remap. That will take certain time. Now in interviews, you can always say monotonic reads can be ensured throughout the consistent hashing of user IDs to the followers. If the assigned follower fails, we remap the user, which might show a brief regression, but then monotonicity is maintained going forward. This shows that you understand the solution and its edge cases, and it's very important if you're giving for L5 plus or a staff level interview. Then the third problem we have is consistent prefix read. This is the most subtle one. Let me show you with a real conversation. So for example, Alice sends a question to Bob that what is 2 plus 2? Then Bob replies to Alice, it's 4. What happens is that what Alice sees on her WhatsApp app is 4 and then what is 2 plus 2? This is confusing, right? Because she sent the message first, but now she's seeing what Bob replied first and then her message second. This problem is called the causality issue, where the sequence is not maintained. Ideally, when we send W1, the right one, after that when we send W2, the right 2, and when we send W3, the sequence should be maintained. And it should not be something like, W2 is coming first, and we are having W1 first, then we are having W3 first. This should not be the case. We should maintain the sequence. Now, let me show you why this problem happens. What is the root cause of this problem? The root cause is something like we have multiple partitions on a database. So something like, now what happens is when Alice wrote, this got copied to partition 1 first. So we had what is 2 plus 2. And then when Bob replied, it got copied to partition 1, that is 4. So in this case, what happened is when the copy of what 2 plus 2 happened, what is 2 plus 2 is copied, it reached the partition 2 after 4. So here is how the sequence got copied. So that is why when Alice read from partition 2, she saw what is 2 plus 2 as second and 4 as first. So this is a causality issue. The sequence has deviated. This is because there are multiple partitions and the replication happened in a different order than originally it was written. Now, how can we solve this? There are multiple solutions. We'll discuss 2 of them. So solution 1 can be causal tracking progress. And solution 2 is single partition for similar. In causal tracking, what we'll do is we'll maintain the previous messages within the same message. How we'll do that? For example, in the previous example, when Alice sent the message, in that we have the Alice v1 and the message. What is 2 plus 2? Now when Bob sends the message, it will have the previous copy and the latest version. So in that, it will copy Alice v1 messages what is 2 plus 2. Then it will have the message from Bob itself, Bob v2, and the message that will be 4. Do you see the difference? Now we are keeping the track of the previous messages and it will be shown at the same order, and whichever is the latest version of the message, in this case the latest version is v2, we will show all the messages in sequence. We will keep the sequence in all the message transactions which we are doing. That way we will maintain the sequence. Another solution what we can do is we can hash the partition key or the partition database and send all the conversation in one database itself. So whatever database which you have, for example, we hash the message ID or the conversation ID and we keep a hash of it. This way we will get the partition of the server and we will do all the conversation in the same partition. Later when the conversation is finished, we will copy it or do the replication. So this way the causality is maintained. Now you may ask that it might become a bit slower, but that is acceptable because we want to maintain the causality. For interview purposes, you can say for consistent prefix read, I'd ensure the causality related data is routed to the same partition or the shard. For example, in the messaging system, all the messages in a conversation thread would hash to the same partition, preserving the order. For global ordering across partition, we'd use vector clock or Lamport timestamp. This is very important. You should mention about vector clock or Lamport timestamp. When you mention this, they will, think that you are suitable for a L5 plus role. If you are interviewing for junior role, then it's fine if you don't mention it. But for a senior role, it is advisable to mention these and it will add some bonus points. Okay, now we are entering in advanced territory. If you understand this section, you are in the top 10% of the distributed systems engineers. Here's the problem single leader replication can't solve. You're building a global app like Netflix or Uber or WhatsApp, and you have users all across US, Europe, and Asia. If all the writes goes to the US East, our Europe users will have a latency of around 150 milliseconds. This is just too much, and this is a terrible UX. So the solution here is multi-leader replication. So instead of one leader, you have multiple leaders. In this example, you see we have 3 leaders, one in US East. So if you see, we have 3 leaders. One is in US East, then another is in EU West, then another is in Asia Pacific. Each of them have their own set of followers. And these leaders are followers to the other leaders. So they essentially replicate from other leaders as well. And whenever a data is written to these leaders, they transfer it to their followers. Now, when do we use the multi-leader replication? Let me show you some of the cases. So the first use case is multi-data center operation. When there are multiple data centers, each data center has their own leader. Then the write goes to the local leader for the low latency, and then leaders replicate to each other, each of the followers which they have. That is of high latency, but that is fine. We are doing it in async fashion. Every read is from the leader of that particular data center. Some of the benefits are the performance. Since there is low write latency because we are directly writing to the leader, the latency is low. Then the fault tolerance. If one data center goes down, then the other continues to be operating. And third is network resilience. Data center can be temporarily disconnected because of network partition. They will resync when reconnected, so that's fine with it. Second use case is offline operation. You must have used Google Docs or maybe Evernote or some of the mobile apps. So when you do the editing on these apps, these will store in your local storage, and your local computer is the leader. Whenever the computer comes online, it will replicate it to the server. So some of the applications are like Google Docs, calendar app, notes taking app like this one. So how it works, your phone is the leader when you're offline, then you make changes locally for low latency. And when you come online, your phone syncs with the server. Each device is its own leader. The third use case is collaborative editing, that is the Google Doc. It is similar to the offline operations, but it involves another level of complexity. This is the online version basically. So when two people or more people are editing a doc at the same time, how do you solve the problem? So in this case, if Alice and Bob are both editing the Google Doc at the same time, each has a local leader, that is their browser. So the changes are synced bilaterally in real time. We have a couple of strategies that are useful for resolving the conflicts, like CRDTs or manual resolution, and many other that we will discuss about later. And many other that we will discuss later in this chapter. Here's where the multi-leader gets spicy. This is time when the interviewer questions you what happens when two leaders receive conflicting rights. Let's take an example. So, for example, if at 2.0 the page title is distributed systems. Now at T1, Alice from the US data center changes it to distributed databases, and the US leader accepts it. Now at T1 at the same time, the Bob from Europe data center changes distributed systems to distributed storage, and the Europe leader accepts distributed storage. Now do you see the conflict here? US leader has distributed databases and Europe leader has distributed storage. Now this is a conflict. Either ways, both rights are accepted by the respective leader and both are valid as well, but they're incompatible. So the system has to choose, and there are multiple strategies and possibilities which we can use, and here we will discuss about those. Now the first strategy is last right wins. This is one of the most common strategies, but it can be a really problematic when there are timestamps that are located in different parts of the world. Here, something like if Alice writes at 1000 milliseconds, the timestamp, then Bob's write at 1001 millisecond, automatically the one with the higher timestamp is chosen. So as per the earlier example, we'll choose distributed storage. But the problem is Alice's write is lost, and this is a data loss. I think this should be used when the writes are independent. So for example, we are using a shopping cart where the loss is acceptable. It's fine, the person can add it again. So that's not a problem. The next strategy is application level conflict resolution. I think this is one of the best strategy, and we can use multiple strategies here. One is maybe on the read and another is on write. So in case of read, that is like DynamoDB style, the databases store both the conflicting version. And when the user reads, the application receives both the version. The application shows to the user there are conflicting changes and which one do you want. And the user can choose in that case. Some of those applications that use it are Amazon shopping cart. If you add an item on the mobile and a desktop offline, both will appear when synced. Another way to use this is on write, but this is used by CouchDB. When the conflict is detected during the sync, it triggers a custom resolution function, and then the function decides either it needs to merge it or choose one of them. So if you see in this code, we have a function called resolve conflict. It checks the priority. If one of the priority is higher, then it will choose version 1. Otherwise, it will merge both the versions. Next strategy, we are going to discuss about conflict-free replicated data types, that is CRDTs. This is one of the most advanced way of resolution. and it is used by one of the most advanced data structures like Redis, React, or Figma for collaborative design. So CRDTs are advanced data structure and mathematically they cannot conflict. Let me give you an example. In case there is a counter and we want to store the values, instead of storing counter A is equal to 1 or 2 or 3 directly, it will write something like this. Increments Alice 3 and Bob 2. That is, the counter has been incremented by 3 by Alice and then by 2 by Bob. Similarly, for the next decrement operation, Alice incremented by 0, Bob incremented by 0. So at the end, it will do a total, that is 3 plus 2 minus 0 plus 0, which is equal to 5. So both Alice and Bob can increment independently. When saying these counts are added. Another example is of setting a value. For example, Alice has set a value for a variable to be x comma y. Then Bob's adds y comma z parallelly. They are doing it concurrently. So inherently, it will decide the conflict and merge it to x, y, z. So here they are merging both the values together by deciding the values from both the users. The next strategy is operational transformation. This is very commonly used by Google Docs. So let me give you an example. Suppose there is a text in a Google Doc called hello. Alice at the same time insert x at position 2. We are considering it 0 index. So 0, 1, 2. At 2 they have inserted x. At the same time Bob sees it and deletes the x. So what will happen is that the OT will check the values and analyze it, and based upon its cognitive intelligence, the final value will be hello. So this is the advantage of using OT. It cognitively decides what to be used based upon the dictionaries it has and the understanding by using machine learning models. Okay, let's discuss about all these strategies and some of the advantages and disadvantages. The last right wins strategy. The advantage is that it is very simple, no need of complex algorithms to be required. But the con is that the data loss. It is used by Cassandra and React. There's an option to choose last right wins while installing Cassandra and React on read resolution. So the pro is that there is no auto data loss, and the con is the burden is left to the user to decide which version to delete. It is used by Amazon DynamoDB. Next is on-write resolution. The advantage is that it is a very flexible kind of strategy. The disadvantage is that we have to write complex logic. It is used by CouchDB. Then the data structure of CRDTs. The advantage is that there will be no conflicts ever. The limitation is that it has a very limited data type. It is used by Redis and React. And then the last strategy is OT, operational transformation. It is great for text, but it is very complex. It is used by Google Docs. If in the interview I have to answer about which strategy to use, I would say for conflict resolution, I'd first try to avoid conflicts through the application design. That is by using partitioning of data so different leaders handle different data. If the conflicts are unavoidable, I'd use CRDTs for data types that support it, like countries or sets or counters. Now for complex data, I'd implement custom conflict resolution on write for storing metadata like vector clocks to detect conflicts, and for applying business logic to merge. The last write wins is a last resort due to the data loss. Now here's the final piece. How do multiple leaders communicate with each other? This is called topology. Let's discuss some of the strategies about the topology. First strategy is all to all. This is the most common one. Here, leader 1 is connected to leader 2, and leader 2 is connected to leader 3, and similarly, leader 3 is connected to leader 2 and 1. They are bidirectionally connected. Some of the advantages that it is one of the fastest propagation and the changes reaches every leader directly. It is also fault tolerant. If one link fails, then the other will still work. The disadvantage is that the complexity. It is a very complex network, and conflicts are more likely because there can be a lot of complex conflicts and we'll have to resolve it every time when it occurs. The next is circular ring. In this, leader 1 is connected to leader 2, then 2 is connected to 3, and 3 is connected to 1. They are bidirectionally connected but not connected to each of the leaders. So one of the advantage here is that there are fewer connections and simpler to manage. Now, the major disadvantage is that if one leader fails, the ring breaks. And if the ring breaks, then the propagation is very slow. If there are many servers, more than 3, there might be 10 of them. In that case, what happens is the change from server 1 to server 10 will take some time because it is going through a ring. So because of the multiple hops, it might take some time. The third style is star topology. There is a central leader, that is L1, and through this central leader, all the other leaders are connected. If you see here, leader 2, leader 3, and leader 4 connects from leader 1, and they collect the data from leader 1. So the advantage is that the routing is simple. Everyone needs to just copy from leader 1 and there is central control. One of the major disadvantages is that it is single point of failure. So if I see here, L1 fails, then every other fails. So that is why then we'll have a new leader election, and then the sync has to be maintained and the application would be in hold. So this is one of the disadvantage of star topology. Now let's see in real world scenario who all uses which type of technology and topology. So MySQL cluster uses all-to-all topology. The circular or the star-based topologies are used by legacy system. It was used earlier, but nowadays it's not used anymore. The modern systems like Cassandra and DynamoDB, they use hybrid topology with the gossip protocols. All right, so we have reached the final boss level, the leaderless replication. This is what Amazon built for their shopping cart. This is what powers Cassandra, DynamoDB, React, databases handling trillion of operations per day. So previously, we discussed about single leader and multi-leader applications. So in a single leader, there is one node that is special, the leader node. And in multi-leader application, or you may say replication, there are few nodes that are special and there are multiple leaders. In this case, we have leaderless. So no node is special. All nodes are equal in this case, and the clients write to multiple nodes simultaneously. It is not one node it is writing to, but they write to multiple nodes or they read from multiple nodes simultaneously. So let me show you the design, how it works. So suppose there are 5 replicas, N1, N2, N3, N4, and N5. And they all are connected as peers. In this, no one is a leader or no one is a followers. All are peers. So how the write works in this case? So when the client wants to write a value, say key is equal to cart and value is equal to item 1 and item 2, it sends the write request to all the nodes in this case. It does not choose a single value. Now, after sending the write request, it waits for a quorum response. Here, quorum means that the majority out of all the nodes. So in this case, if you see there are 5 nodes, so the majority will be 3. So it will wait for at least 3 acknowledgements that the write has been written, and once it has got the acknowledgement, it is considered as successful. Now, what about reads? Reads are similar to how the write works. So the client sends a read request for the value key card. Now the client wants to read the right value and it should be optimal and the latest value. So what it does, it waits the response from the quorum. So the responses might be different because the replication would or would not have happened to all the servers. So in this case, the client, when it gets the response from all the servers or the majority of the servers, it uses the latest version numbers or it uses the latest timestamp. This way, the client decides whichever is the latest version, it receives that response. Now, why this method is very powerful compared to the other methods like single leader or multiple leader. Let's see a scenario. So, suppose there are 5 servers, okay? One of the server fails in this case. So when someone fails, we can do one thing is that while writing, we are not supposed to mandatorily write to the specific node. We can skip that node for the time being and write to rest of the 3 nodes. So out of 5, if node 2 has failed, and earlier it was writing to node 1, node 2 and node 3. In this scenario, it can choose node 1, node 3 and node 4 instead of node 2 to write the data. Similarly for the read, if one of the nodes fails, instead of reading from that specific node or server, it can read from the other server as well. That is why it is very special. No failover process is needed, to bring the leader up. No leader election is required that will waste a lot of time. And then the system continues operating seamlessly. Now, which all systems use this type of replication? We've already discussed about Amazon DynamoDB, which is powered by AWS. Then Apache Cassandra, it is used by Netflix, Apple, or Instagram. This also uses Leaderless replication. Then ReactDB and Voldemort by LinkedIn. Voldemort, not the Harry Potter one. It's the one designed by LinkedIn. Let me show you how this actually works in real time. Now the magic of leaderless replication is in quorums. Let me explain the formulas that we use in quorum. Consider n as the number of nodes that are number of replicas. Then w as the number of nodes that must acknowledge the writes in a quorum. Then r is the number of nodes that must respond to the reads in a quorum. So the formula is w plus r is greater than n. If we follow this formula, we give the consistency, we give the high consistency, we make sure that we have the latest data that we are writing to, we read from the latest data that we are reading from. Let me give an example. So here there are 5 servers. So for example, if a write request has come to this one, we want to write some value. So it will go to server 1, server 2 and server 3. After we have got the response from 3 servers, then it is considered as successful. Similarly, if a read comes, then it makes sure that at least 3 servers responds to the read request. Then only the read is successful and it takes the maximum or the latest version of the value. So according to the formula, here we see we have w is equal to 3 and r is equal to 3. So w plus r is 6, which is greater than 5, the number of nodes. So this is following the formula, or this supports the quorum formula. Now, if you write to 3 nodes and read from 3 nodes, at least one node appears in both the sets. So, for example, we are writing to node number n1, n2, then n. We are writing to n1, n2, and n3. Similarly, we are reading from n2, n4, and n5. So if you see, there is an intersection of the node. So this formula makes sure that there is an intersection between the number of writes we are doing and the number of reads we are doing. So that is why we make sure that we have the latest value, and this is how it happens. So for example, if we do writes to 2 nodes and we read from 4 nodes, that is a must for us. In this case also, W plus R is equal to 6, which is still greater than 5 and follows the rule of the quorum. In that way also, we are making sure that we are having the latest value. Usually this configuration, the configuration 2, is primarily used if we want faster writes and we are okay with the slower reads. Now let's take another configuration where we do W is equal to 1 and R is equal to 1. You see that the sum is lesser than equal to 5. Now this does not follow the quorum formula, which was W plus R should be greater than N. Now because of this, it does not guarantees consistency. Usually we use this configuration if we are okay with eventual consistency and we do not want a strong consistency. Let me show you some of the configuration. Now if we want a strong consistency, we will do equal number of writes and reads. That is, if the number of servers are 5, then we will make writes equal to 3 and read is equal to 3. This way it is balanced and we have a very strong consistency. We can use this in banks and other high consistent application. But if our application is a very write heavy application, so what we can do is we can reduce the nodes we write to and we can increase the reads we are going to do from. So in this case, if you see, we have reduced it to 2 and we have increased the reads to 4. So still it is equal to 6. So 6 is greater than 5. So fast writes and slower reads. Now if we want an application which is read heavy, such as in the case of social media, we are reading a lot than writing. So what we can do is we can reduce the number of read nodes as compared to the write node. We can increase the number of write nodes. So we make sure that the data written is consistent, but we want faster read. So that is why we have reduced the number of reads. Now for eventual consistency, we can make 1 to write and 1 to read. Although the sum is 2, which is not equal to the formula, which does not satisfy the formula of the quorum, but we still use it some places because we are okay with eventual consistency. Now here's what candidate miss. The formula W plus R greater than N guarantees you'll read the latest write, but it doesn't mean you'll never see the old data. Let's look at one of the edge case. Now for t is equal to 0, client A writes v1 to server n1, n2 and n3. So at the same time, at t is equal to 1, before the replication completes, client B reads from n4, n5 and n1. You see what's happening now. The replication hasn't yet completed. It means that at n4 and n5 the value hasn't yet reached. But at n1 the value has reached. So if n4 and n5 haven't received the value v1 yet, but n1 has, so client B gets v1 from n1, v0 from n4 and v0 from n5. In this case, the client picks the higher version. That is, it uses the latest version. So it will use the value from server n1. This is how we solve the problem of non-replication if the data is not yet replicated. That is why version numbers are critical. For a leaderless system with n replicas, I'd configure quorum as W plus R is greater than N to ensure the consistency. For example, with 5 replicas, W is equal to 3 and R is equal to 3. This guarantees that there is an overlap for at least one node in the read set and will have at least the latest write set. The trade-off is latency. We are waiting for 3 nodes instead of 1. For read-heavy workloads, I might choose W is equal to 4 and read is equal to 2 to optimize the reads. Now guys, have you considered when we are writing and the node is down? So what do? We might use hinted handoff. So here's where the leaderless replication really shines. Let me show you a production scenario. So here is a scenario in which we are writing to replicas n1, n2, n3, and n4. And for instance, n2 goes down. What do we do in this case? Now the client wants to write key user 123 and the value Alice, and we have a quorum of w is equal to 3. It means it needs 3 successful writes. The problem, as I already told, n2 is down and the clients can only write to n1, n3, n4 and 5. Only 4 are available in this case. What do we do in this case? So the solution can be a sloppy quorum. Sloppy quorum, instead of requiring writes to the designated replicas of n1, n2, n3, we accept writes to any available nodes. Now the clients can write to n1, n3 and n4, 3 nodes. So the quorum is reached. This is called hinted handoff. In this, what happens is n5, this temporarily stores the data for n2, and whenever n2 comes up, it hands off the data. So in this case, we had a dedicated set of writes that we can only write to n1, n2 and n3, and then replication happens to the other servers. In case n2 goes down, n5 is chosen as the new server, which is a hinted handoff. It stores the data for n2 as well, and whenever n2 comes up, it copies the data back to n2. So if you see here, in this case, whenever the server is down, it starts to write to n5, and when n5 detects n2, it copies it back. This is what it's explaining in this case. Now, some of the benefits of this form is that it makes a system highly available. So the system accepts writes even when the nodes are down. Now, it forms eventual consistency instead of strong consistency. The data eventually reaches the correct nodes, and no manual interventions is required for automatic recovery. In this case, whenever the system auto recovers or the server auto recovers, automatically the data is copied, so we don't need any manual intervention in this case. Now, there are some of the trade-offs which we are dealing with. So if we want a strict quorum, that there are designated servers from which we will accept the write acknowledgement, in that case the consistency is guaranteed. But now if we use a sloppy quorum where we can write to any nodes, in that case this is called eventual consistency, and we might see older data that would be temporarily. So depending upon your use case and even way, like you want a strict quorum or you want a guaranteed consistency, or if you are okay with eventual consistency, you can opt for which type of quorum you want. Now let me take up some of the real world scenarios. So in DynamoDB, we use sloppy quorum plus hinted handoff. In case of Cassandra, it is configurable. You can choose which one you want. You want a strict quorum or you want a sloppy quorum. In case of Rax, we use hinted handoff extensively. So the sloppy quorum prioritizes availability over consistency, which aligns with the AP side of CAP theorem. For use cases like shopping carts or where availability is critical or eventual consistency is acceptable, then this is ideal. For financial transaction, I'd use strict quorum, even if it means rejecting writes during the failures. The final challenge in a leaderless system is detecting the concurrent writes. This is the hardest part. Let me show you the problem. Now, for instance, at T0, client A writes a key page with value V1 to N1, N2, and N3. At T0, another client B, writes key page and the value V2 to N3, N4, and N5. You see N3 in this case and N3 in this case is common. Now that is a conflict because they are written at concurrent time or the same time. Now what do we do? N1 and N2 has value V1, N4 and N5 has value V2, but N3 has a conflict. So here we are going to discuss some of the solutions to solve the concurrency problem. The first solution is last write wins with the timestamp. So in this case, for example, if V1 is written at a timestamp 1000 milliseconds and V2, there is a very small change. That is, it is written at 1001 millisecond. In that case, we choose the timestamp which is on the later side, which has come later. In that case, V2 is the winner and we choose that. But there's a problem with this because of clock skew. There can be different servers who are present on different time zone. And because of that, we cannot decide rightly which value has come later. Let's go to another approach which is much more better, that is the vector version. Initially, the value at n1, n2, n3, n4 and n5 is set to 0. Now, the client A writes value for V1. So it will be V1 and the counter has incremented to 1 in N1, N2 and N3 because it is writing to 3 servers. Client B concurrently at the same time writes the value of page equal to V2 in servers N3, N4 and N5. So it has written page value as V2 in the 3 servers. So when reading, we compare the vector version in this case. If one vector is strictly greater, then the newer version is used. So in this case, vector V1 and V2. V2 is greater than V1. So in this case, V2 will be used. Now, if the vectors are incomparable, for example, if we get V1 and V1, then in this case, it's a concurrent, right? And then we have a conflict. How do we solve that? In this case, the final answer is that the system returns both the values to the client and the client can decide which one to choose. You might have seen, in your conference talk or in Amazon cart that sometimes two people are working at the same time. It gives you two options as available, version 1 and version 2. And then it asks you which one you want to discard. So this is the ideal way where you can ask the client, and this is called manual resolution. Now let's see which all databases uses which solution. If we go to React, they use vector clock. Now Cassandra, it uses LWW by default, but you can use LWT, that is lightweight transaction, for stronger consistency. For DynamoDB, it strictly uses vector clock internally. Okay, so for detecting the concurrent writes in a database where there is leaderless system, I'd used versions of vector. So unlike timestamp, version vectors are immune to clock skew and can precisely detect the causality. When conflicts are detected, I'd either use application level resolution or CRDTs to automatically merge. For Cassandra specifically, I'd enable lightweight transaction for critical data that requires the linearizability. Alright, we've covered a lot. Let me distill this down to what you need to remember for the interviews. The big four: single leader replication. This is the foundation. Master this first. Use synchronous for critical data, async for everything else. Know how failover works. The interview question can be like Instagram photo storage, replication lag, read your writes, monotonic reads, and consistency. Replication lag, read your writes, monotonic reads, consistent prefix. This is where good candidates become great candidates. The solutions can be sticky sessions, reader routing, or quorum reads. Some of the interview questions can be, why might a user not see their own comment? Third is multi-leader replication. This is used for global application with multiple data centers. The conflict resolution is the hard part. We can use CRDTs when possible, custom logic when necessary. The interview question can be design a collaborative editing tool like Google Docs. Fourth is leaderless replication. This is for maximum availability. The quorum formula will be W plus R is greater than M. Sloppy quorums trades consistency for availability. The interview question could be design a shopping cart that never loses data. So the progression of single leader to leaderless isn't about better or worse. It's about trade-offs. Single leader simple, consistent, and single data center. Leaderless, complex, available, and multi-data center. You can pick the right tool for the job. In interviews, always ask what's our read ratio? Then what's our consistency requirement? Are we multi-data center? What's our availability target? These questions shows that you're thinking like a senior engineer, not just reciting algorithm. If this helped, smash the like button and subscribe. Drop a comment telling me which concept clicked for you. And hey, if you're preparing for FAANG interviews, check out my system design course in the description. I go way deeper in these topics with real interview walkthroughs. See you next time.